Hello, in today's video we will talk about operational amplifiers. The operational amplifier, otherwise known as op-amp, is a special component that has a vast level of applications. Our op-amp usually comes with a non-inverting input, inverting input, two DC power supply leads, so here's our non-inverting, inverting, and our two power supply leads, so there'll be positive and negative, and a output terminal. As well, some op-amps will have a special lead for other purposes here. At face value, the op-amp works as so: if one terminal of the op-amp is higher than the other, then our output will favor the higher value. So if our non-inverting terminal, which is the plus, the positive end, is higher than our inverting terminal, the negative, so this is V plus V minus, then our output saturates more so than the positive supply voltage. What I mean by this is, if we take, for example, here we have a non-inverting amplifier, so if we had a signal coming in through here, V in, and so this is connected to ground, this is obviously higher than this, so we have our input here, we have a short spike here, nothing, a short spike again. Our output will look something like this. So as soon as it hits the spike, we have a flat period, from here to here. It's higher than the ground, and if it's lower than getting from here to here, lower than the ground. So it's essentially saturated its voltage supply limits. And if you remember from a transistor video, the saturation part is what's hitting its max limit. So this is what it's essentially doing here. And if we had our inverting amplifier here, so say they're going in through here, it's coming, we have our spikes again, and we'll get in the output is something like this. This is mimicking that, except the polarity has changed, it has reversed, because it's an inverting amplifier. So you get the opposite signal you've put in. So say if we may want our op-amp to not just produce full flat voltages, we may want to amplify a signal instead. And here I have is an inverting amplifier in this configuration. And by having this feedback resistor right here, we can adjust the gain of the op-amp to our liking, and this prevents our op-amp from saturating. And V out, so just for a inverting amplifier, so inverting amplifier. It's inverting because we have our signal going to the minus, as opposed to the negative section. We can use the formula to find out V out is minus RF over R in times V in. And this is how much gain we will get from our signal from the amplification. So it's not only these type of AC-like signals we can boost, we can also do the same with DC voltages. And we'll take a look in MultiSim on how we can do that. Before we head off into MultiSim, let's confirm with our calculation what our expected values will be. It's always better that you know the theoretical side of these things instead of just placing it into a simulator, because then you would know roughly what you're expecting from your simulator. If you just plugged it into I suppose if you just plugged it into a simulator, not knowing any foundational theory or the basic theory of what you are doing, you would not be able to know what is right and what is wrong. And so as an example, let us take Rn equals 3.3k, Rf equals 10k. So we want to find our V out, so our expected voltage output here. We'll plug in the numbers using this formula. So minus 10, 3.3. I did not put the like 10,000 since we're working the same units. We can just more or less cancel it off. Times, so our V in, we can set a V in of 2 volts as a good example. So say we're putting 2 volts into here. This is 3.3k, this is 10k. We'll plug that into our calculator now. And we arrive at minus 6.06 volts. I will now load this circuit into MultiSim and we'll see what we get. So I've got our circuit up in MultiSim. I've put in the values of what we've done in the example. We've got our inverting amplifier. We've got our Rin is 3.3k ohms. We have our RF, our feedback resistor, is 10k ohms. And we've got the voltage probes here to see. Just gonna run it. And as we expected, we got 2 volts in, output negative 6.0605 volts, as we expected. So our calculations are correct. And this is just to show what we could do with an inverting amplifier. And of course, this is probably going to split up into two parts. I'll show you an inverting amplifier and a non-inverting amplifier with given examples. A very important formula to know within op-amps is a formula which relates to its input voltages and its voltage gain of the op-amp, which is V out equals AO, which is the voltage gain, V plus minus V minus. So this is our voltage gain. These are inputs, and this is our output here. This is a formula for an ideal op-amp. And for an ideal op-amp, it suggests that it behaves like a voltage source and it supplies voltage to this equation. So an ideal op-amp, what would happen is essentially we have our, I'm playing as V, but we have our, it's behaving like a voltage source here, and we do not have any impedance here. Well, this idea would be 0 ohms, but realistically we do have some impedance, so we do have some impedance present in the op-amp. And this is not a realistic drawing of an op-amp whatsoever. This is just to let you guys know. But we're not going to dive too much into that. It's just to make you aware of it. I've got some few defined rules for op-amps, and we'll get right into that. So we have some defined rules for the op-amp. Rule 1. Ideally, the open loop gain AO equals infinite, but the gain is really 10 to the power 4 to 10 to the power 6. So there's not an infinite gain we can keep going up to. This is the realistic. Rule 2. For an ideal op-amp, its input impedance is infinite. So as we said before, there's really nothing. But in reality, we do have a set value, which is between 10 to the power 6 to 10 to the power 12 ohms, and for the output impedance, we do not have 0. We do not have 0. Ideally, we would, but we'll probably just have 10 to 1000 ohms. So this would be the input output impedance, ideally. No, sorry, the realistic. Rule 3. The input terminal of an ideal op-amp draw no current. Reality, this is kind of true as it draws picoamps to nanoamps, which we could probably round up to 0, but that's not always in certain situations, so keep in mind. And rule 4, I'll read it to you now, I'll further explain this, it'll make sense. When we have negative feedback in place, this is when we have our output of the op-amp connected to our inverting terminal. And when the op-amp senses a difference between its inverting and non-inverting inputs, the response we get back from this is that it sends as much current or voltage through the feedback network to keep the difference between our two input equal to 0. So, just remember this. I'm going to soon explain what this means, but keep this in mind. So, if you remember that inverting amplifier circuit we had just simulated in MultiSim and calculated, that feedback resistor was our negative feedback. Apologies on the atrocious handwriting, but it is what it is. And you may have noticed that the formula I told you before had not factored in anything related to feedback. So based on what rule 4 was saying, you know, this is giving a fraction of the output back in here into this terminal, into our inverting pin terminal as feedback. And our formula, if you remember, has not said anything about that. It's just factored in, oh, V out is equal to our gain multiplied by the non-inverting voltage minus our inverting voltage. But because we are now factoring in feedback, we can change this a bit, and we arrive at a new equation where we can say the voltage gain V equals minus F minus, and this is the feedback that's being factored in now into here. And hopefully this gives you more of a basic idea of how negative feedback is working. What's really interesting is that we can even simplify our op-amp circuits with negative feedback, and for how that rule 4 came about. So if we were to treat this op-amp as an ideal device, we could rearrange our equation. So our equation here we can rearrange that to this. And because we are treating this as an ideal device, this side will equal to 0 because ideally we want the gain to be infinite. And then we are just left with V plus minus V minus, and if we haven't factored in the feedback, whatever, this will equate to 0. as it's trying to simplify out. It's trying to simplify out, you know, make things the same. It's trying to do as much as it can to make its two inputs the same. So when that happens and we substitute its two inputs, we get a 0. And this is how the rule 4 came about. Before we end off this video, I'd like to show you the formulas for an inverting amplifier as well. I've shown you before. This is the gain, and the gain for a non-inverting amplifier. So for a inverting, gain equals to V out V in, which equates to minus R2 over R1. This is our gain. And if we, like our formula before, if we times our voltage input voltage in, then we could see the final voltage output. But this is more so our gain, how much we times our original input. And the gain for non-inverting is gain equals V out equals to R1 plus R2 over R1, and this equates to 1 plus R2 over R1. So I'll be splitting this op-amp topic into a few parts. Maybe we could tie up everything in the next video. But as well, there is quite a bit to cover, and I'd like to show more. We're going to cover a bit more on the inverting amplifier, a bit more on the non-inverting amplifier. We're going to show a bit more examples on what circuits we can do with them. Like, it's not only, you know, there's different types of op-amps. I'm going to explain to you that there's a bit more to them, show you a few examples. Then yeah, it'll be quite interesting. So hopefully, before that, I showed you these equations just in case you want to do a bit more if you want to do some self-study or learn a bit more. But yeah, and hopefully you've learned something, and thank you for watching, and do take care.